I'd start on this session 4 on molecular imaging in cancer and neuroscience. We have 3 presenters. The first one has a broad overview. I will introduce him soon. And the other are more focused on some very interesting technology, which is available here in Bergen and might make a breakthrough in cancer research and also in other kind of research related to molecular imaging, mass cytometry, sorry. So we are now being much more molecular, but we will have an introduction first by Klas Pettersen. He is a CEO of NORA, Norwegian Artificial Intelligence Research Consortium, and he is also a previous researcher and maybe even an active researcher in the GLILE research group at the Institute of Basic Medicine Science in Oslo. So he has a perspective both from the AI in Norway as the head of NORA, and also experience from computational neuroscience at the Department of Institute of Medical Bioscience in Oslo then. So he might be the best to give us some perspectives on AI in neuroscience and medicine in Norway. And by this, I will welcome Klas to give his talk. And I think he will keep on for about 40 minutes. So it's a very broad perspective we'll get now. And look very much forward to this. Thank you.
Thank you, Arvid, for a very, very nice introduction. I will see if my, no slides come up. Thank you. As you said, Arvid, I will take a broader perspective on this. And I, as you said, also have a background from the Faculty of Medicine at University of Oslo. So I will also show you some examples from my own research. NORA, first, I will say just a couple of words about NORA. NORA is the Norwegian Artificial Intelligence Research Consortium. That's a collaboration between 7 universities in Norway and NORS and Simla within the field of artificial intelligence. Artificial intelligence, machine learning, and robotics. And NORA has been up and running for almost 2 years, so it's rather new, but still absolutely. And we have done quite a lot already, and we are here to kind of make collaborations within AI between our partners to strengthen research, education, and innovation within artificial intelligence. Today, I will talk about, I will take the broad perspective then. I will say a little bit about the AI history. I will also go through a little bit of AI theory and especially deep learning then. I will show you some examples from my own research and the big data area that we're in now. I will go through deep medicine and recent examples from healthcare, both kind of internationally and also in Norway. I will say a little bit about mobile devices and health, deployment of AI in healthcare, and I will also talk a little bit about NORA and healthcare. So let's go back to the beginning then. I like to start the beginning of AI in 1950, where Alan Turing proposed the question, can machines think? And this was kind of the advent of course, computers, modern computer science and artificial intelligence. And just after 1950, a group of very well-known scientists in the field proposed a workshop. So they sent in a proposal for funding for a workshop, and there they described that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. And this was, the proposal was sent in 1955, and they had this workshop through the summer of 1956 at Dartmouth College. So this is kind of the founding fathers of artificial intelligence, really, and this is also where the term artificial intelligence was coined. So that's kind of the background and the idea. And the idea was then to kind of simulate intelligence and make intelligent machines. And if you go back to the early days of deep learning, then this is not a new field. I mean, a lot has happened the last years now, but this goes back all the way to 1958 and earlier. Already by then, McCulloch Pitts had proposed some simple models of neurons. And Frank Rosenblatt then invented this Perceptron, which was really a machine to simulate them and to predict what, for example, they could predict image, what was in images. That was at least the goal. But they built this inspired by the brain. So the Perceptron worked in a sense similar to neuron. It was built up of units that, similar to neuron, summed up input. And if this sum was big enough, then it sent a signal to the next unit. So this is pretty much how a neuron works, right? While summing up inputs and sending action potentials if the sum is large enough. This made extreme interest also publicly. So this is from the New York Times, where they wrote that the Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So very big words, of course, and too big, absolutely. So what happened later on was this AI winters. So the field was hyped, the expectations were way too large, and this kind of ended in, many people say that we have had several winters. So the first winter was after this hype in the 60s and started maybe in the 70s then. And then that meant that few people were doing research within this area. Funding dried out, so it was not easy to do any good research in this area. And the attention was to other fields of computer science. And we have been through a couple of these winters where we have a hype. And of course, right now you could also say that you may have a hype in the field. I mean, it's a lot of attention about AI. And the big question then is if I could still keep my Hawaii shirt and summer hat on. If we are in the summer and will continue to be in the summer during the next years, or whether a new winter will arrive. So my take on this is that things are different now. In the 50s, 60s, 70s, AI was actually not working very well. The Perceptron by Frank Rosenblatt didn't work, actually. First, they thought it worked. They thought it could discriminate between, for example, military equipment and other equipment, or cars, military vehicles and private vehicles. But it showed later on that all the images from the military vehicles was taken on a certain day with bright lights, and the other images of private cars they were taken on a more kind of dim day. So actually it didn't work. It only predicted brightness and darkness. But these days things are starting to work, at least. Some of us actively use what you can see here, this speech recognition, natural language processing, which is behind the Siri, for example, or Google Home and other tools. Amazon has the same. If you go into your web browser, everything you do there, or not everything, but much of what you do is based on AI. When you get recommendations from Google or from Facebook or YouTube, or if you use TikTok, the young generation typically use that. All your recommendations are based on AI algorithms. So I will go through a little bit about what has happened in the field and why it is so. But first of all, this bigger term of AI, that includes a lot. AI is typically about mimicking human intelligence, so it's advanced problem solving. And a subset of AI is what we call machine learning. That includes techniques that enable programs to improve at a task, so it's typically learning processes then. And a subset of that, again, is the deep learning that has caught a lot of attention lately, and which I will talk more about now. And this deep learning, deep kind of reflects an artificial neural network, which has several layers. So to the network to the left there, you have an input layer, and you have an output layer, and in between you have just one layer of these artificial neurons. But to the right, you see many layers, and this is basically just a definition of a deep network. And this increased in popularity at least from 1989, where Jan LeCun and co-authors showed that this back propagation algorithm was working very well, and that they could kind of decipher handwritten digits, zip codes from the US Postal Office. And these networks, they, as you said earlier, typically have many layers. In each layer, you do different processes. You have convolution, where you kind of have summation rules of neighboring pixels. But typically what happens is that, for example, if you have an image, you take each pixel in the image, and that image, the color in that pixel has a numerical value. So this is just a huge matrix, or it could even be more matrices. If you have 3 colors, for example, which builds up the whole spectrum. And then you process these numbers and do different kind of typically non-linear processes to these numbers. And then in the basic layers, you typically could detect, for example, edges around the counters. You will typically see edges around this bird here, and so on. And the features get more and more complex. And at the end, then, you will predict whether this is actually a bird or whether it is a dog, for example. And the network is built up in a way such that if your prediction is right, then everything is good and synapses are strengthened. And if it's not right, you will change some weights of the synapses. So synapses are then the weights between these artificial neurons. And similarly to the brain, they are weakened or strengthened to improve the whole algorithm. So from 2012, you saw a quite huge leap in deep learning. You have this yearly contest. It's called the ImageNet Large Scale Visualization Recognition Challenge. So this is a contest where you could submit your code, and the code will then try to find objects in images and what kind of objects you see in a classification task of objects in images. So in 2012, the winning algorithm, which is called now AlexNet, made a quite huge leap in how it could predict all these images. So and what had really happened was that it used an 8-layer deep network, which was quite deep at the time, but a big advantage of this algorithm was that it started using the GPUs, the graphics cards. So these processes can be done in parallel, and this kind of increased the compute quite a lot. So this was in 2012, less than 10 years ago. If you then just move to 2015, it was not 8 layers, but it was suddenly it was another network structure then, but it was 152 layers ResNet. And then already by then, this recognition task, it was on a human level or above. So the algorithms in 2015 were on a human level. So quite a lot has happened. This is just a few years ago, right? And the models, they get larger and larger. If you see here, you see an overview of kind of the development in the field, where you see typical Moore's law. If you scale that to the how much compute you need to train a network, you will see that from 2012, actually, it's much steeper than Moore's law. So the networks get larger and larger, and you need more and more training, more and more computer power. And this is kind of the basics of deep learning. You need algorithms, you need compute, and you need data. And all these factors have improved hugely the last years, especially, of course, data with the internet, and especially also GPUs. And not only GPUs, get more and more tailor-made computer chips for artificial intelligence and deep learning. So Google used the TPUs, for example, and a lot of these big companies now have tailor-made computer chips. So this has hugely improved the last years. But then the question which is important here maybe, so will artificial intelligence actually change health or healthcare? And the answer to that, I think, I wrote this in Tidsskriftet for Norske Legeforeningen less than 1 year ago. And the answer there is yes, I wrote that. That's my perspective on this. And it's actually happening now. So the development is really fast, and a lot of things are happening now. This is written in Norwegian, so I just want to say that if you don't read Norwegian, you could try out this Google Translate, which is artificial intelligence, and it actually translates the article quite nicely. I will show you first some examples from my own research, and then go on to show you examples from other labs and around both internationally and around Norway. But this is what we did at the Faculty of Medicine in the group where I worked. You see to the left the mouse sleeping, and you see activity. This is 2-photon microscopy. So what I want to emphasize here is the big data thing. So for this one project where we studied sleep and how these special cells called astrocytes, we studied their role in sleep. From this project, it led to 50 terabytes of data for one research project. So this is a lot, and this also has exploded lately. And if I think back to when I started programming at my Commodore 64 in the 1980s, a lot has happened in one generation or through the last decades. So 50 terabytes of data, it takes a lot not only to process that, but just simpler things like storage and how to retrieve data and so on. A lot of challenges. And also we are proud it made into a good journal, but not only that, I guess this will be the first and last time in my career that our research went into the front page of VG. So that was just a little bit of self-promotion there. That's kind of the top journal in Norway, VG. Big data, 50 terabytes. And what do we do? Well, we used a bit of traditional statistics, but what we also do is to develop algorithms to find specific patterns. So what we do here, that's kind of also a newer project also, but we also record, in addition to the 2-photon microscopy imaging, we also record the extracellular potential, the local field potential. It's kind of an intracranial type of EEG. And we detect pattern in that. So what we wanted to do was to look at learning processes in the brain, because this is actually something that the brain does quite different than the deep networks, the artificial networks. The brain is quite efficient, but it learns differently because we don't have any back propagation of signal through the whole network. So what we wanted to do here was to try to study this, and something called sharp wave ripples are important, shown to be important for learning, and we wanted to detect these patterns. So there we also used then a deep artificial neural network to detect learning patterns, so to say, in the brain, in order again to improve the deep artificial neural network, the learning algorithms. So this is kind of a loop. So the brain still inspires artificial intelligence. If you look at how this deep learning and machine learning has developed the last years, you can see that it has exploded. If you do a search in PubMed, you'll see that machine learning, it has just this really exponential increase with the doubling about every 2.5 years, and deep learning even steeper after 2012. So this has kind of been introduced and highly applied also in medical research. And as an evidence for this, actually my wife is a pediatrician, and she is, I would say, almost allergic to computers. But this weekend she was on a digital conference as well. And it was quite fun for me to see then that in pediatrics also, one of the talks that she attended was about artificial intelligence in pediatrics. And this was also nice to see because it was at the Massachusetts General Hospital, Harvard Medical School, where I also spent some time actually during my PhD in the lab of Anders Dale, which is a famous Norwegian in radiology department at MGH. Then he's in San Diego now. So it was quite nice. So this is it's kind of impacting the whole field, and it's coming into the medical science, not only medical sciences, but also even down to pediatricians here. One of the most influential books, or also maybe persons in what we call deep medicine now, is Erik Topol. So this is his book from 2019. I highly recommend that. And if you do not have time to read the whole book, at least you should read his paper there about the high performance medicine. So there we kind of summarize the field, what has happened lately, and also his perspectives on the future AI in medicine the coming years. So I will show you some examples also from Erik Topol. I would also recommend you to follow him on Twitter if you're on Twitter, because there he posts papers almost before they're out in the journals. So that has been kind of a good news feed for me in the field. The last year he has focused also a lot on COVID-19, but he has focused on artificial intelligence a lot. So some of the papers I will show you and projects I will show you now is actually found from his Twitter feed originally. So I will go through then some examples of how deep medicine is used, or how artificial intelligence is used within medicine. Here is Nature Medicine this year in review, where they show that in a systematic review that machines match humans in image-based diagnosis. I'll just go through this rather quickly, some examples, but I will then I'll go on to show you a little bit of projects in Norway. Here is another example. Was the December edition. The whole 2019 December edition of Nature Methods had focus on deep learning in microscopy. Here is an example from JAMA Cardiology, high throughput, contact-free detection of atrial fibrillation from video with deep learning. And this was actually from video of faces. So I could actually see the heartbeats and you could actually see atrial fibrillation from video on faces. So this also, of course, artificial intelligence and the deployment of artificial intelligence opens also a lot of ethical questions and considerations. Surveillance is one of them, of course, but also this kind of black box problems that the code gets so complicated, so it's hard to see which kind of basis the code kind of uses for different decisions. So in decision making, for example, one thing is diagnosis, where you want maybe the best tool, but sometimes you really also want to understand why. And the why question is important, and it's a non-researched field within artificial intelligence itself, explainable AI. I will not go more into that now, but this is also interesting and an interesting topic. Here, an example from PNAS, expert level detection of acute intracranial hemorrhage on head computed tomography using deep learning. I will move on. Let's see. Next is here, automated abnormality detection in lower extremity radiograph using deep learning. This is a Nature Machine Intelligence paper. Here, precision screening for familial hypercholesterolemia, a machine learning study applied to electronic health counter data. So, of course, not only imaging, but also text. I mean, artificial intelligence is also good at text. You see now a lot of projects very automatically read journals, extract important information, find patterns, and even also could propose diagnosis from medical records. Here is a prediction of the stability of natural and de novo designed proteins. I will come a little bit back to this because I will also mention really also a giant leap, I think, in deep learning in protein folding that came out last week, the AlphaFold. I will come back to that. Here, a systematic approach to clinical oncology uses deep phenotyping to deliver personalized care. So here, it's a perspective article. They have a review article. They show how all kinds of information actually could go into this and then make precision medicine better. Yeah, I think I will just skip a couple of slides, but to get the picture, a lot of good research are now out. It's still mostly research. I mean, you see a lot of problems when you want to move the algorithms from one lab and a certain equipment and to move that to another hospital or another lab with another type of equipment. So all these things are hard. So we're still in the kind of early age of deployment, but the research is clear. You will find this more and more also out in the clinic. You will see now that typically, for example, in image recognition, they typically are on the level of humans. It's still, I mean, deep learning still is not perfect, absolutely not. And also they have false predictions, as humans also do. But typically human together with these tools, I mean, humans and algorithms typically do different errors. So a human being using this tool is, of course, then the best way to go around. Yeah. I will There are many groups in Norway, many health groups, many good health groups. You also know this in Bergen, also at the Moon Center, applying artificial intelligence to medicine and healthcare. I will just mention a few. One is to the right here is Håvard Danielsen and the DoMore project. Which applies deep learning to oncology then. To the left here, you see a group from the machine learning group from the University of Tromsø, especially Robert Jensen there to the left, which have had several really interesting projects, both on image recognition, but also on text. So they use artificial intelligence for predicting post-operative delirium. It should also be mentioned that this group, Robert Jensen, is now also they was awarded the Center for Research-Based Innovation in Tromsø. This is called Visual Intelligence. It's a pure artificial intelligence project, but then especially focused on medicine. So this is interesting. This is a huge project. Some other groups within the NORA partners that do exciting projects. Here is from an example from the University of Stavanger, a project called Safer Birth, where you have on the newborn get these sensors and they predict, or they help out both kind of, they do both image recognition actually of what happens after birth, and then they do analysis of fetal heart rate signals, and all this in order then to increase the survival rate, of course. Another group doing working a lot with AI and healthcare and medicine is in a big insight at the University of Oslo. By the way, in NORA, we have a Friday afternoon webinars at 2 o'clock, and a lot of them have been focusing on AI in healthcare. Here is Arnoldo Frigessi from Big Insight explaining their modeling. They have done modeling with respect to coronavirus spread in Norway in collaboration with Folkehelseinstituttet. So this has been important tools for the last year now, and also used as decision tools for Folkehelseinstituttet. Here you see some examples from Simula, which is also turned into a company called Ager, where they also look at colorectal cancer and polyps. Then I want to run fast forward again. Christian Arnfinsen, we like to think of him as a Norwegian, but I think he was born in the US, but in a Norwegian family. In 1972 proposed that the protein's amino acid sequence should fully determine its structure. So this has been how kind of proteins fold has been big challenge in the community, and also a lot of people have tried to simulate this. And just last week now, Google DeepMind came out with very impressive algorithms based on deep learning, where you to the left here see proteins and see that it's almost perfectly predicts the structure of proteins. So this will be an important tool. Here you see how kind of the last years, you see the score where 100 is the maximum, and how this has developed from 40 and now up to 90 for this new AlphaFold algorithm. And that means that it's almost on the level on experimental errors. So when I saw this, I was thinking I was quite impressed. This is an impressive project, but could we actually do this in Norway? I was thinking. And at least if you look at the projects, some of the really huge projects in deep learning these days, we couldn't do those in Norway because they required too much computational power actually. But this they did. It's a large project. They used 128 TPUs. These are the kind of graphic cards of Google, and it was then run for several weeks. But it's in the size that Norway actually could do. The data are freely available, so this is a very good example of how freely available data is important to the field of deep learning. Then, so the data are available. I think also know that they haven't revealed the details of the algorithm at all. But I think it would be possible if we were able to kind of get the brightest minds in Norway into this project to do a similar project in Norway. So this is so if you have some ideas, just contact me. This would be very interesting to do actually. Mobile health, so to say. We have a lot of this is actually from Apple front page of their web pages these days, not long ago at least, the iWatch, where they say the future of health is on your wrist. So you see this, that all the big tech companies, they are now going to health. It's a lot of data out there. We will get more and more data. The new watch here has some kind of ECG things and also oxygen meters. So you could gather a lot of data. And this can also, of course, also be used actively in healthcare. I recommend this paper by Ida Sim from last year in New England Journal of Medicine about mobile devices and health, and how this could kind of be used. Of course, if you have it need to be stored in a safe and good manner, but then in principle you could then deploy together with public health records, artificial intelligence tools. This could be important information for disease and prevention of disease. So let me then skip to the market thing. Is this kind of mature enough? Well, it's, again, we're in a very exciting age. This is just happening now. So it's only in 2018 that the first algorithm, AI algorithm, was approved as a medical device by the FDA in the US. And this first tool was done about diabetes retinopathy, which is kind of, you take an image of your retina and you could predict whether you could then have this blindness disease. And there now you see that AI tools are better than experienced doctors. And it's also democratized healthcare, right? Because now this tool can be used almost by anyone. So in a sense, you don't need to go into big city to get a diagnosis. This could be done in a rural countryside in whichever country with less experience, at least health personnel. In Norway, we have also done a lot of background work. Vi have stortingsmelding on helsenæringen. We have a national strategy of artificial intelligence. And also the Directory of e-health in Norway has this white paper on AI applied to the health sector. So we have a lot of basic documents in Norway. I think in Norway we are quite good at a lot of things, especially health data. So here is kind of a readiness index where you see on the vertical axis there is kind of the readiness when it comes to data, where Norway scores extremely high. We are not that good on the other axis, which is more on the technical aspects of applying AI and deep learning. But we have kind of a really good foundation in Norway to be good at AI in healthcare. We also have a really many great research group. you now see this helseanalyse platform and health analysis platform in Norway taking form. This is being built now, making health data more available for research and actually also for the industry later on. So it's exciting times in Norway. The AI communities in Norway are better organized. Data are good, and we also get better and better kind of machines and equipment. So in this report, they conclude that they encourage a closer collaboration between academia, industry, and units in the public sector to create a good, fast, and robust development in the field. So this should be a priority in Norway, and also in NORA we try to do this. So we have, inspired by this report here, tried to make collaboration across all these mentioned partners. So we will also now apply the European Commission for becoming a European Digital Innovation Hub, where we have a lot of really great partners, both Norway Health, Oslo Cancer Cluster, Helse Sør-Øst, and Medical Imaging and Visualization Center at Haukeland, University Hospital, Oslo University Hospital, Akershus. A lot of really good partners trying to create this environment in Norway for AI and healthcare. So this is an application. Still, please contact us if you want to be a partner on this project. So this was a little bit of this and a little bit of that, a lot of different kind of things, but I hope you got a broad overview about AI in healthcare, AI in general, and specifically AI in Norway. And to conclude then, I think the research results show that AI technology is quite mature when it comes to research. Norwegian health data is a potential gold mine. We have great data in Norway. Long time series, also the cancer registry, for example, back to mid-1950s is complete. Norway have expertise needed, I think. AI solutions had just started now diffusing into the industry and into patient care. Norway will focus on building a coherent infrastructure to stimulate research and deployment. This is the health analysis platform that, and we need an effective innovation and deployment ecosystem. So that is what also NORA wants to be part of building up in Norway. But I actually think that given kind of the foundation in Norway, given where we are now, I think Norway could become a European lighthouse within AI and health. So that's my take-home message. Thank you very much.
Thank you, Klas, for a very inspiring talk, going both deep and wide. I think you are ready for some questions, and Stefan will take care of that.
Yes, thanks very much also from my side for this great talk. And we have a number of questions from the Discord already, but I actually want to start with one of my own, which is, how much do you think is the progress, in particular in deep learning, attributable to just basically better hardware, better computational power? In particular, I draw my experience from the field of computer graphics, where one can argue that most of the fundamental problems were solved by the 1970s already, but it took another 20 years or so until we now have, due to the power of GPUs, we have photorealistic video games. And in fact, some of at least the success in deep learning is actually based on GPUs being cheaply available. So is it just that, or do you think that there were some major problems overcome that had not been solved by the end of the 80s, let's say?
Yeah, you hear that a lot, that this kind of progress is due to hardware and data and only that, but I don't agree at all. You see also enormous development in the algorithms. You have a lot of new deep learning methods now that didn't exist some years ago only. So the huge networks now, of course, data and TPUs or GPUs, they are a requirement to be able to apply deep learning. But you have a lot of new algorithms. Transformer networks are now huge, and also kind of course, some of the like back propagation, which is kind of the way networks typically learn, that has been around for many years. But you see different network structures. You see new additions to the algorithms. So it's also an algorithmic development in the field.
Thank you. I have a question here from Hauke, and he relates to maybe the black box nature of deep learning as it is sometimes seen. He asks, image-based deep learning seems to do something similar to classical feature detection plus statistics-based classification. Do you think that the benefit of better classification scores now outweighs the problems that are caused by the black box nature?
It depends on the field. If I wanted to be diagnosed, I would rather be diagnosed by a better tool, which is then proven to be better in a scientific way. So when it comes to, for example, diagnosis, I have no problem with the black box, actually. But of course, when it comes to applying this as a decision tool, it could be, for example, it could be anywhere. If you want to make a decision that require an explanation. If I want to apply for something for building a new thing on my house, and then this is only automatically processed. I want to have a decision that explains me if the answer is, for example, no. So it depends very much on the fields, and of course, explainable AI is also a huge field and is also improving. But it's not that we should have a problem with black boxes in general. It depends on the question.
I think this also somewhat relates to a very interesting question that Helvig had. And he writes that we usually refer to machine learning supported image classification as a success story. But in real images, we actually have multiple objects or even multiple parts of an object that we wish to pay attention to. How do we bake that question of what in the image should be considered into the target for classification, for instance, in this popular competition? And it basically means that the answer of what is in an image can be answered in different ways, depending on the context. We have some audio issues. Did you get that last part? Okay. Hang on a bit, if you can hear me. We have some.
Right, it's more about kind of asking the right questions, maybe. Of course, these days you could have AI tools find every object in the images, but that may not be interesting to you. So if I understood the question right, it's more about asking the right question. How could we trust an algorithm, maybe, when you don't kind of understand what it is looking for? I don't know if I got the question right there.
Partially, and also that, I mean, when trying to classify objects, I mean, it's always the question, I mean, we as humans are evolutionary biased to recognize certain things. Well, an algorithm may, just based on how the problem is exactly set up, pay attention to very different things. So how can we sort of bridge this gap?
Yeah, that's really true. And you see, for example, a lot of image recognition tools, they pay an enormous amount of they focus much on, for example, the texture, the material, and not that much maybe on the shape. So you certainly have a lot of ways to improve the existing algorithms. They do kind of use other feature detectors than typically a human would do. So this is an interesting question, and also again a very interesting research area actually, trying to get it more human-like, but maybe also not as human-like as we would think. I mean, humans are so good at finding patterns that we find patterns where typically there is no pattern also. So that's also why we can why we are good at this thing called few-shot or one-shot learning, that we can predict something without needing to train a lot on it, because we find these patterns very well. But this could also fool us sometimes.
Maybe we have time for one more question, at least, from Frank. Thinking about the lack of ability in terms of facial recognition that we have seen popularly in people of color, different ethnic backgrounds, and the problems in also automatic translation of Asian or Arabic languages, do you think there is a risk of having AI third world countries relating to different regions or ethnic minorities not being able to enjoy the benefits of AI to the fullest extent?
Yes, absolutely. And this is a big concern. It's not about the algorithm. It's typically about the training data, and we should pay a lot of attention to these problems, because the training data are important. And if you have some kind of bias in your training data, the algorithm will continue and maybe also strengthen the bias. So this is a concern that should be on the top of our heads, and it's we are able to deal with it. It depends typically on the training data. So if you get good enough training data, the algorithm will also behave well.
Yeah, I'm sorry, I think we did get your response, and maybe we can have one last question from Ingrid, just because it's sort of a more high-level question that relates to the things that we are discussing here at the fundamental level. What do you think are the main obstacles for a successful implementation of AI-assisted diagnostic and predictive tools in a routine a hospital setting, including regulatory restrictions, limited knowledge about the potential benefits? How do we move forward, essentially?
I think it's one thing you mentioned there, regulatory restrictions. Those are the kind of the first questions to get into. It's even new also internationally. The FDA approved this first tool in 2018. So this is new. It's new. I mean, if you get an algorithm approved, could it then continue learning or not? By now it could not. And then if you get a new version, how should you kind of in a more easy way get this defined as a diagnostic tool? So we have a lot of juridical things to sort out first, and then I think the big problem is kind of to transfer what you see as good research results at one scanner, maybe in one research group, into a more kind of general working algorithm across hospitals, across scanners, and so on. So these are huge research fields now, and important.
With that, I think we thank you very much for your talk and for the discussions here, and we move on to the next speaker.